Welcome everyone for HPC, the first lecture 1, High Performance Computing, our part 2. We will talk a bit about HPC ecosystem technologies, and in the last part we really motivated a lot of terminologies. So what is basically a multi-core chip? And in this part now we will explore a little bit what the many core difference is, but also aspects like shared memory has been discussed, distributed memory has been discussed, and also the importance of interconnects, that the systems are very tightly interconnected and also motivated. Of course, it's the power programming of those machines to make it then really a high performance program application on these systems is very something which is a little bit special. So hence we have lecture 2, 3, 4, and 5 just talking about this. With MPI, the message passing interface, with the OpenMP shared memory standard. But then we learned also that AI is another type of application we also have to consider for HPC today, mostly for two reasons. Firstly, we can train much faster the model, right? So in terms of just an old workstation running maybe for 3 or 4 days. But the second more important part is we have hyperparameter optimization at scale. And the kind of performance of the AI models relies in the parameters of the models. And if you can do hyperparameter optimization at scale, you can do much better parameters for the AI models, and with this, much better performance, much better accuracy, or lower error rates, if you call that. So this is also not obvious. We will see how that materializes in lecture 6 and 7 when we talk about deep learning. There will be one of my experts from the PhD program, Marcel Ach, talking about hyperparameter optimization for a whole practical lecture for you, so that you really get the benefits. Hence, HPC is used for traditional physical sciences. For instance, as we discussed, numerical methods based on known physical laws. How an airplane is flying is basically nothing else than physics. The same was true in the video, as you have seen with weather forecast, climate models. So let's switch a little bit to the second part, which should sort of build to it and also add some elements to it and more deeper insights to it, like AI. We will look a bit more what deep learning really means and so forth. It's another terminology aspect that you should know. First of all, is to understand, when we have now seen all the Lego bricks, right, that you had in the first part, how that should all play together. And for this is incredibly important to have system software. System software is something which we consider different parts. So one would be the operating system. That's something you already know from the last practical lecture: Unix, Linux derivatives, Scientific OS, CERN OS. There are different operating systems around that are used on these machines. Often this is a sort of reduced Linux, because you don't really need a complete full-flavored Linux that you use on your laptop. But in many cases, this is basically a Unix, form derivative. That's why we called about this. But more importantly also, and this is basically something we will have in our practical lecture 1.1 next week, scheduling systems. We have seen now these large systems like in the video, right? This was number 1 in Europe, the Jubil system. Or Lumi is now the number 1 in Europe, the Finnish one. They are used at the same time by many, many researchers, right? So basically, we call that a scheduling problem, because everybody wants to access the system now. But of course, the system has limits, right? So not everybody now can really access it. Hence, they have to do something we call batch queuing. They have to queue, right? Like here, when you go to the pharmacy or somewhere, you get your queue, and then it's your turn when they call your number. I think Iceland implemented this fantastically. It's actually in all the shops, right? So that's quite interesting. Hence, we will talk about scheduling, how it is working, that so many people have a so-called concurrent access at the supercomputer at the same time, how that works, how we schedule their jobs, their applications, their algorithms. There are technologies like Slurm. This is a bit outdated. Sorry, that should be Elia, of course, and the deep test cluster. They have scheduling systems in place. Another one is monitoring systems. So once you have basically all the users in, important is also to have ganglia systems and also monitoring systems that really look what is happening on the systems, and provide, of course, examples here in the course, and also see, are there certain racks which are, for instance, dead, or let's say not operating. This could be the case that, for instance, CPUs were overheated, right? They're very densely packed together. So every now and then in this large HPC systems, you have broken hardware. it's overheated, or the interconnect fails for some reason. So there are lots of errors in the system because you have a huge system. We will talk about this also when we talk about uptime and basically elements of having as much as you can 99% performance always on uptime, so almost used. But of course, in practice, it's almost not achievable with HPC machines. However, they're very costly, so there should be also an operation as much as you can. So different examples like LLView we will look in. Ganglia, again, is a very known one. Again, here, this is more rather for the Elia clusters and others. Doing parallel programming forces a lot of problems and challenges for the programmer. As I said, it's not anymore having your Eclipse environment, doing a bit Java programming and then running it. You want to run it on 500,000 processors or on 2,000 processors. That's already challenging enough. And then you basically see that with the way you program it, because you still have a source code, but the source code should run at the same time at 500,000 processors. So when these interactions with send, receive, and so on will be incredibly complicated. Hence, there are tools and technologies in place called performance analysis tools. So they will instrument your program and will basically identify bottlenecks where you see, okay, the interconnect actually cannot throughput your data anymore. You programmed in a way that basically it's not possible to scale it up to 2,000 processors. So these are all different, let's say, important ingredients to get really the most out of a HPC system today. And as we have more and more also challenges of programming them low level, high level access methods are also coming very popular more and more. One very known one is Rescale, for instance. It's a so-called middleware on top of the HPC systems, which has already many applications ready for you to use so that you don't have to necessarily go with SSH in, module load, etc. Instead, you would have a Rescale software. We look at all of those, of course, in the course, right? So that's the overview. As you see, the most essential tools that you would have in HPC. Of course, maybe the first and foremost essential is your own code, your own algorithms, right? That you then use in combination with these system software tools. And I should also a bit, let's say, motivate the more newer approaches to this. So we talked about the batch queue. You have to wait a long time before you get scheduled and so on. There's also a certain way of interactive supercomputing more and more where you don't necessarily need SSH keys. If you remember, I was also showing that a little bit in the practical lecture where we have Jupyter notebooks nowadays on the HPC machines. So Jupyter is something which some of you know from Google Colab. Have you used Google Colab perhaps by chance? So some of you, where you have a much more interactive, let's say, GUI, where you can really work with files and can write your source code, run it, and so on. So that is getting more and more supported. We will also use it in the course to access deep here and there. And this is not at all very simple for HPC. Hence, you see here lots of middleware takes place. The details are not so important, just that there's a really stepwise approach to, let's say, navigate around the SSH access, right? As I told you last time, SSH is incredibly important for getting access. Now I tell you no SSH key, but this means also there's lots of technology in place to make that happen. And of course, you need to be also known before as a user. We will also talk about this much more in Practical Lecture 1.1 and others, where we talk about this. And this enables sometimes, like here, a respiratory analysis where you really can move the visualization during the computing. You can do, let's say, more interactive ways of interacting also with your application. That's an important part of it and motivates a little bit this, but it's not supported in all the HPC systems. So chances are when you go to an HPC system that you have access to, it's not yet supported. In Lumi, it has been just coming online. In Jülich, we support this on the majority of systems, but not at all, because it's quite let's say, very hard. But it's important to realize that this access is also there. Now, when we talk about system architectures, there's a lot to also realize. I mean, first of all, there's lots of vendors which go in, like Cray. They actually went away. They were not on the, let's say, horizon of HPC for a long time. Now they're back again. And there are lots of elements, like you here see a nice supercomputer BlueGene Q that was once in our halls. It's not existing anymore, this architecture type, right, from IBM. So as I said, again, from the top 500 perspective, from the lifetime, it's really fast, right? Formula One, whatever is old technology, what's really not working will be not funded. And with this is very quickly out of date of HPC. Could be used in conventional computing in some companies maybe, but it's not relevant for HPC. And this includes, of course, the cores, so the really computing, the capabilities in terms of threading, memory access, data access. So it has many ingredients. That's why the HPC system you have is not really just putting a CPU in, connected with the internet, and you're done, like you would say more or less with your laptop. It's also not completely true with the CPU internally, but these are much more complex systems. And on top of it, you have also in the architecture an impact of the different vendors, right? So NVIDIA, for instance, was just, one example that we have seen in top 500, very, very famous. But nowadays we have AMD, right? For instance, Lumi, the supercomputer, has no NVIDIA cards. It has AMD cards as accelerators. This has an architecture impact, but also in programming impact. So you cannot use CUDA, which is the modus operandi for instance, programming NVIDIA GPUs. You have to use another toolkit. And with this, you can go on and go on. This is an important part of it. It's a multi-million business. Hence, NVIDIA is top-notch in the moment, as we know, maybe not forever, because AMD and others are following suit. But it's a way where the vendors have a very strong impact in these designs. The other part we should not forget is you need infrastructure for it. You cannot operate, let's say, here on the floor, suddenly all these racks. You need a specific gas, basically, if there's a sort of fire. We have seen in one of the videos that actually this is not only one floor. There's a second floor, usually that high, where the cables are, where the water cooling is, where some elements are water cooled these days. Sounds interesting, but we will see how that materializes in one of the lectures, where you put the CPUs in liquid cooling, right? So it's also nowadays happening. So you have lots of infrastructure impact for these elements as well. And you need usually a very, very good hall, or nowadays also even containers, where you really deploy these systems. And that all basically has a big architecture impact. Now, again, I told you BlueGene is basically out of date. So it's not anymore existing. But the beautiful is what I got here from the EVM slide is really the idea of how you now have the terminology created, right? You start essentially here with a small chip, right? And when you put them together, then you have a module, and then you have something called a compute card. That's how you create a supercomputer, right? Then you have many, many, many of them, and you have a complete node that you can stick in and stick out in this rack. And we will have a chance to go to UTS, to the system that we have, to see a little bit what we mean with rack and node cards and nodes and so on. But this is basically just as a normal CPU, as everything begins, also in our laptops. But the point is it's tightly integrated and very dense integrated, because of course you want to have a whole hall of it, right? So hence you will add on to this complexity. Once you have, let's say, half a rack, what we here call midplane, you have a rack, then you basically have these different nodes where you then have maybe, depending on the size of the system, many of them. What you don't see in these beautiful diagrams is, of course, lots of cables, right? They are all interconnected with each other, as the video was suggested, right? Hence, they are basically also network topologies about different hierarchies where we differently will explain them. Dragonfly is a very modern one, but we'll come to this in later lectures. Just to think again that this technology, this kind of terminologies would be a bit important to understand. Racks, what basically are these kits, these big things. And then still what integrates is all this kind of smaller elements that we already know from traditional computer science. We just put them more densely together. Putting them more densely together means more errors, more heat, more problems, right? So the chances are if you have thousands of GPUs in one rack, that of course 1 or 2 CPUs get, crack over time. And then you have to exchange the node card, the compute card, depending on what is broken. The interconnect will have problems. The connect to the data storage will have problems. Hence, these systems are still, let's say, every now and then also not always fun to work with, because especially in the beginning, they have lots of problems, and over time mature to a very high uptime. Good. Coming more to the network side of things, because I talked to you a lot about the elements of network interconnect is important. How that looks like is a little bit explained here. Here you would have, for instance, a torus where every CPU is basically connected to the other one. And if you think about weather forecast and you want to have the rain over a certain element, simulated, then you really want to basically exchange how the weather moves from one core to another. Hence the interconnect here. The data that you exchange should be really like this, right? To the next level, then next time step of weather forecast, next time step of weather forecast. And every time we will shift the data. So this is a very, let's say, simplified view, right? Now, when we get to a very huge computing system, this is not going to work always. We have some switches in between to go to other big, let's say, parts of the system, or as it is here also to go to the data storage. Hence, there will be dedicated nodes just working for data and will not basically do computing. And today we can say even, and that's an important part of this slide, that we have the bottleneck in the data. So for us, basically, we don't have really any more troubles in computing. We could have the big hole, buy tons of CPUs unlimited, tons of GPUs unlimited, but that will help us, because in the end, we cannot fuel the GPUs with data enough. We cannot fuel the whole CPUs with data enough. So the architecture is mostly limited basically by the throughput of data today. Hence, we need new technologies to work with data in the future. Otherwise, we will not getting, let's say, the next evolution of computing. Hence, cloud computing is doing it a bit differently, but also quantum computing is a new technology where this is solved completely different, and we will make a small point of it also in one of the lectures. So take away the message that today the network data bottleneck, also with GPUs, is one of the hardest trouble we face. Coming now to the architecture elements, we have now heard about the multi-core CPU. It's important. More and more with AI on the horizon. I'm sure you have heard about it, deep learning, machine learning, and so on is on the vogue. We have these GPUs that are just very beautiful for it, right? We have seen NVIDIA cards are quite, prominent today. And they came out of computer gaming cards, interesting enough, so GeForces and so on. But here we're talking about really those which are used for scientific computing, but it's basically the same concept. But nowadays we see with Hopper architectures, or we see Ampere already really tensor cores in it, which are very oriented towards deep learning. And we'll talk about this in later lectures. There's a very specific type of architectures as well that you could integrate, like these field programmable gate arrays. We don't cover them a lot in the course. Here you really program very hardware-oriented with circuit-oriented designs. So it's something what we don't really face, but also can give you incredible performance if you have very specific elements. So let's understand a little bit the GPU. Who has used the GPU? Probably all of you. If you don't know, maybe your laptop has even one inside the system, right? So to understand it from the bottom up is basically that, first of all, unfortunately, you need a CPU, right? The main memory. There's a question. There's a question here in the audience if a graphic card should be used for scientific visualization or a very specific one. And this is a very loaded question, actually, because the newer ones, the GPUs, Hoppers, and so on, they miss sometimes some elements that you need for rendering in the visualization pipeline. So they're actually not any more usable for visualizations. Hence, the point is because they are oriented towards deep learning. And we may make a case for it. TensorFlow, they have limited instruction sets, not supporting anymore the visualization. So what basically is modus operandi that you have a couple of visualization nodes, which then support your simulation and visualization of it, while the number crunching or AI, for instance, is done on very specific parts of the GPU. It's the evolution of the NVIDIA cards, for instance, that they go more and more away from visualization, because they want to more general compute, to do TensorFlow, kind of deep learning algorithms very efficiently. Another point of it is the precision. Instead of double precision, single precision, nowadays we see them with half precision to do more speed. And we have learned in AI, it doesn't make a difference. In physics applications here and there, it does, to have double precision. but not for several problems in AI. They have a regularization effect. You anyway regularize over time. So in this sense, it's a good question. You need probably in the future really this modular approach of saying what we do in Jülich. We have a complete cluster for visualization very closely as a module at the supercomputer where you rather would do your visualizations. But this is alluding to where basically these graphical chips come from, that you have basically lots of different processors. And here we now really talk in the hundreds and thousands. Now that is a bit contradicting what I told you before. When you have so many processors close to each other, overheating, right? So what is the trick? What many cores are doing? They have a low single thread performance. You could say that the heartbeat of these are very slow, right? But because you have thousands of them, you can have incredible throughput of simple tasks. So they're not anymore the physics number crunches that we have in the CPU. Hence, they will also not be used for every problem. You have seen in the video, we still need our cluster module. We still can benefit from the booster module. The booster was the GPUs and the cluster was the CPUs. And this is something what we will also explore then with deep learning and so on. And although it came from graphics, what I just said was, basically having rendering pipelines in your graphic, gaming cards that you had before. The Tesla series and others that followed, like also the different architectures, Volta, Ampere, Hopper, that we will review in lecture 6, I think, is it? Then we basically will see more we optimize towards really general computing and away from visualization and these pipelines. But the idea of the visualization pipelines, the kind of sort of smaller computing parts, are inherently in doing this. Now, lots have happened in the years since this was started from NVIDIA. Also, this is an important part. Nowadays, we have very specific device memory that we will talk about in lecture 6. And we have to always bypass basically this device memory and go to the CPU, which is one of these bottlenecks I meant, right? When you want to do a lot of data processing with GPUs and you have 5,000 of it, that's okay for computing. But what we often face is you have a data throughput problem of loading actually the data these days. There are some interconnects to go from GPU to other GPUs directly, NV links and NV switches within a node. From NVIDIA, for instance, but then across the nodes is getting already a bit complicated. And we will talk about it in lecture 6. Important is that you take away the message that this is a different architecture part for a single, computing entity, which we call a many-core, basically GPU. And this is important between multi-core and many-core, right? Many in the sense of thousands, but very low frequency. So you can put thousands of them very closely dense together without bit errors, without being, overheated. But because you have so many, you can use them very nicely. And why you can use them very nicely is best explained in this. What means acceleration? I boiled down the problem to a little bit here, where you see this is just a bit of threads programming. But let's say you have just a couple of cores available in this machine. You can see that some of the problems, and this will be important to understand in deep learning, you can very nicely, again, chop them down into smaller computing, which is independent computing. And this independent computing is a part of many core, which is perfectly supported. You see here, for instance, an underlying technique in deep learning algorithms is matrix vector multiplication or matrix multiplications, etc. But the way how mathematical that is done, it chops down the matrix and vector here in this color coding, and you can compute the result here without ever knowing what these fellows do, right? Just the color is known. Hence, you can chop down this big problem. Let's say you have a very huge matrix and a huge vector into smaller pieces, solve them embarrassingly parallel, as we would call it, or nicely parallel, not talking to each other, and put that just in the memory. And the whole result will be then the big matrix vector multiplication that we have then as a result. So essentially, that means we have this kind of throughput now that we would have in clouds on a bigger scale inside the GPU. And this is exactly the underlying sweet spot why deep learning is so beautiful, for instance, with this. Of course, deep learning is a big topic. We will have one lecture about it where we basically mathematically just partly address why this is now, so important to use in GPUs. But here are some other examples where you then also will understand a little bit about deep learning architectures. They make, again, use from this through convolutions, for instance. But whenever a deep learning network, which is explained here a little bit, again, we have a whole lecture 7, right? In a couple of practical lectures, I will introduce you to deep learning, machine learning. You will then basically see that through this kind of architecture, what you do mathematically is nothing else than smaller mathematical operations, smaller convolutions, smaller, multiplications really to learn from data, signal processing. And with this, GPUs are just beautiful for it. Also important to understand is that deep learning doesn't mean you have neural networks. Some of you maybe know neural networks, normal neural networks, artificial neural networks, a little bit. That was basically like 2 hidden layers. Deep learning doesn't mean that you just extend those to 500 layers and are done with it. We will learn in deep learning that we have also very specific architectures. So convolutional subsampling in convolutional neural networks. We have long short-term memory networks, GRUs, gated recurrent units, where let's say the sweet spot is also in the architecture, how you do it and how the architecture of the neural network is. They are deep, but it's not just like a typical old artificial neural network. And now we have 50 layers. I think I explained that a little bit here in the video. For you also as an appetizer, it's a very hot topic, deep learning. And there are lots of jobs outside that we actually will discuss also in the epilogue of the course. But we're not there yet. So let's have a look a little bit how that works. And you have seen, sorry for the online audience, maybe not catching everything, but I was explaining a little bit the video here indoor. The long story short is that deep learning networks are very smart networks these days. They have very dedicated layers, they have very dedicated functionalities, and we will talk about it basically also in lecture 7, and we'll also then, of course, make the case why GPUs, why high performance computing is really needed for them to really work with them. And no matter where you are, in remote sensing is one of our research where we do satellite data. You can imagine satellites that go across every day, and basically day and night, they collect a lot of data. And there you basically have then the different architecture parts here where we can work with these huge and big data sets. So when you think about it, we will talk about applications in lecture 7 as well. And we have, of course, lots of research in this area. If you're interested in this application field, also let us know. One sweet spot I just want to explain is that apart from the architecture we just saw in the video, there are so-called hyperparameters, something called learning rate, which loss function I use, how the filter layers should be looking at. So how big should basically the idea be in the different filters? These are all things which are not obvious. You have to pick them, or basically pick a network that has defined them. But here relies the performance or the accuracy of your deep learning network, right? This is incredibly important. We call this a network architecture and network architecture search. In the other words, hyperparameter optimization, to go with these parameters systematically and find those which have the best accuracy, is another big part in high performance computing with RayTune, for instance, Optuna. They're different, let's say algorithms also, but Marcel Ach will be one that I invite for you to basically then also face this. And this is really a part where HPC again wins and helps not only with faster training of models, but better models that can be done with a laptop, for instance. Just some relationships. Here we will talk about also that deep learning is really having this footprint in computing. We will make cases why, because there are many different parameters. Of course, when you are not swimming in big data, then you better should not go the deep learning way. Hence, our traditional deep learning models that I use and others are still support vector machines, older models, because if you don't have big data, then chances are that deep learning will make no sense. There's data augmentation, there are other technologies, but usually you're here somehow in a space where random forests and SVM still have good performance. But also this can be parallelized today with high performance computing, but then the impact is not anymore here. We also will discuss in one of the lectures with large language models. You have heard about this with ChatGPT. We have a new big research project, me and my fellow colleague Hafstein Einarsson, and we will talk also in one lecture about this large language models, how they work and why they're basically here, right, in training time. Huge of parameters, very big data, and so on. Just to motivate that you can break down some of these applications also with other technologies. I think that's for completeness, so that everything is maybe not necessarily always with HPC. We do also cloud computing a lot in remote sensing, where you use, for instance, Spark, Apache Hadoop or Spark. Have you heard about this maybe by chance? Okay, some of you. This is also a very popular technology, Java stacks, which are very known, but this is also, again, something we don't focus here in the course on. We would take this parallel computing to the course we have in fall. Just some relationships also to the data. I mean, actually with Grindavik now, we have probably a very accurate case on that with, the earthquakes first and then lava flow and so on. The more accurate we do now these domains, right? When we simulate this with HPC, the more data we have in the terms of, here you see a terashake domain, so an earthquake, and a petashake that is really then, so to speak, having the kilometer much more dense. And we have seen the inner scale and the mesh points really of the accurateness, how we basically would simulate this much more towards the reality. But if you do this, you pay the price significantly of growing, for instance, from terabytes of data sets to petabytes of data sets. Hence, another motivator why we sometimes have to go also to HPC. It may be not always a computing intensive part, it might be the data part why it motivates this. And also for some of you that maybe not, again, know the speed, which is an important part to realize that basically we have very slow disks and so on. And the main memory is already something which is very, let's say, fast compared to it. But today also the level of caches and so on, until you go to the heart of the CPU, plays a certain role in applications. Hence, this cache hierarchies are important for CPUs. And you will also see that memory, HBM in NVIDIA cards is also a very important part of it. And we will talk about this also throughout the lectures. And really need to also make a case that big data means also something for HPC as a motivator. Hence, we have again this tier systems, how it begun, but also, as you have seen in the video, a module for data analytics with much more memory than other systems. We have a module for storage with a parallel file system. So we will talk about how we can access files and write into files in parallel with 100,000 processes. So all of these things are matter of HPC, and we will talk in the different lectures about it. Mostly thinking about a more hierarchical storage, a more weight, basically how you accumulate storage and so on. Yeah, the modular architecture just put again motivating that I talked a lot about cluster, booster, storage, and data analytics are also part of the game, right? So that should be also considered when you do this. Finally, just to think about a little bit what's happened here in Iceland. Again, things I had also already in the practical lecture the last time. There's a data and simulation data labs. If you have interest to maybe join one or want to work with one, and one of these, let us know. And history should be not forgotten. Some of you will see in HPC maybe praise. This is now more or less still active as a user group and user forum, helping also us in EuroHPC on the user front, representing users. But nowadays, the EuroHPC joint undertaking is basically taking over many of the elements of praise. And Iceland is part of it, right? We were not part of praise before, but now we are part of EuroHPC. That means also we can get lots of computing power if we need it. The quantum computing is just one slide saying there is a video if you have interest. Many students ask me about quantum computing. This is a complete different way. I gave a UT Messan YouTube video is there, invited talk, but also lots of publications. But this is more an advanced topic, but you have seen it's already on our horizon. We do lots of research around it. And it will be perhaps one module somewhere in around this HPC system in the future. But this means not anymore 0 and 1s, like we have the bits and bytes. This means we have 0 and 1 at the same time. So lots of complicated computing. And I don't want to stress this in this course, just that there are lots of elements outside. And this is something where we already have practical experience and real computing power. I leave the video for you as homework. It's a bit long to play now. I will play it here, but you don't have to be here. You can have this downloaded at home. So I would say that's all for today. Thank you very much for being here. Be patient, and we see us not on Monday. This will be another pre-recording, right? So 8 o'clock, deal with other things. So, but we will have the probably in-person lecture next Tuesday.